Hi everyone, so this is where we last stopped 2 weeks ago, and we ended off here at subatomic particles and magnetic field, and that brings us straight into isotopes and radioactivity. So the atomic mass. The atomic mass is referred to as the proton number of an atom. Therefore, it is the sum of the protons within the nucleus of the atom. The isotopes are atoms which have the same atomic number but a different atomic mass. Alright, due to larger amount of neutrons being present within the nucleus of the atom. So we have an example here. We have carbon 12. So we have the isotopes of carbon. Our first isotope is carbon 12. And what we realize here is that carbon 12 has 6 electrons, 6 protons, 6 neutrons. Therefore, it has a nuclear number or a mass number of 12. Okay? We have our carbon 13, where we have 6 electrons, 6 protons, and 7 neutrons. Therefore, we have a nuclear number or mass number of 13. And we have our carbon 14, where we have 6 electrons, 6 protons, and 8 neutrons. In each of these, we see that the neutron is what increases, and the protons and electrons stay at 6. These are isotopes of one another. Therefore, the proton number in all of these, the atomic mass in all of these, is going to be 6. However, the mass number is going to be different because we have 6 plus 6 give us 12, 6 plus 7 giving us 13, and 6 plus 8 giving us 14. The mass of an atom is so small that it cannot be measured. And therefore, when we are using relative atomic mass and we're comparing the masses of atoms, we compare the mass of that atom to the mass of a carbon 12 atom. Alright, the mass of an atom, so the relative atomic mass is defined as the mass of an atom when compared to 1/12 the mass of a carbon 12 isotope. Alright, and the isotopic mass is when, and the relative isotopic mass is when we take the mass of a single isotope and compare it to 1/12 of a carbon 12 isotope. So these are really important definitions that we will have to know as we go on. And so we go into the mass spectrum. So basically, the mass spectrum allows us to detect what we have in our sample, and so this is how it operates and how it works. The mass spectrometer, our first thing is that we have to recognize is that our sample within our mass spectrometer is vaporized. We have a vaporized sample within our mass spectrometer. The element is bombarded with a beam of high energy electrons, which knocks one or two of the electrons out of the belt that they are in and converts them to positive ions. Alright, and then our next step, so that's our first step. Our first step is ionization. Our next step is acceleration. The acceleration is where we have the positive electrons being accelerated by an electric field into this electromagnet here, where they then go through deflection. So step 1, ionization. Step 2, acceleration. Step 3, deflection. And deflection is where the ions that we have, the positive ions that we have, are passed through a magnetic field and deflected based on their mass and their charge. So what we should note and what we should remember from our first class is that the smaller the mass of the charge, the smaller the mass of the ion, the more they will deflect. So if you have a if you say, let's say we have an ion that is 1 and an ion that is 2, the ion with the mass of 1 will reflect will deflect more than the ion that has a mass of 2. Alright, so after deflection, our ions go into detection. So this is where the ions are detected by an instrument which is attached to the amplifier and recorder that we have. So we have our amplifier and our recorder chart here, and when we do this, we see that we get a relative abundance of what was inside of the sample. So what do we do with the calculation, with the values that we've gotten from our mass spectrometer? So this is how we work out the calculations, and this is our example question. So the question reads, the mass spectrum of a chlorine atom shows the relative abundance as follows: chlorine 37 as 25% and chlorine 35 as 75%. And we're supposed to calculate the mass of chlorine. So what we'll do is that we'll work through this. So our first step is to list off what we have. We have chlorine 37 listed as 25%, and we have chlorine 35 and that is listed as 75%. So what we're going to do is put our percentages as a number out of 100. So this will be 25 divided by 100, a fraction, and 75 on 100. Our next step to find the relative abundance of chlorine will be to take our fractions that we have and multiply it by the mass number that we have. So for chlorine 37, it will be 25 on 100 multiplied by 37, and this will be 75 on 100 multiplied by 35, and we add these values together to get a total of, let me just calculate it, 35.5. And that would be our relative abundance of chlorine. Alright. Next slide. Not all of our calculations will come with the numbers given to us. We will have to sometimes we will get the graph sometimes. So this one we have here is for boron, and so I filled in the spots, I filled in the values here that we have here. So we see that so we see on this side we have relative abundance, and we have M divided by Z, which means mass divided by the charge of the electrons. So the first question we have being asked here is that based on our graph, how many isotopes do we have for boron? So we have 2 isotopes for boron. So we have a boron 10 isotope and a boron 11 isotope. Okay? And calculate the relative abundance of boron. So we'll basically do the same thing. So we have that boron 10 has a relative abundance of 18.71%, which will equals to 18.71 on 100, and we have that B11 is equals to 81.3%, which is equals to 81.3 on 100. Multiplying both of those, so what we will get will be 18.71 on 100 multiplied by 10 plus 81.3 on 100 multiplied by 11, which will give us a relative abundance of, let me just calculate, 10.814. All right. So radioactivity, our next topic is radioactivity, and so first we seek to define radioactivity. And so some of these isotopes that remember our one of our first definition was isotopes. Isotopes basically, as we remember from like 5 minutes ago, is that we have an atom which has the same amount of protons and electrons, however we have a different number of neutrons within our nucleus. Some of these isotopes are unstable and the nuclei will spontaneously break down, and this breakdown of the nuclei is referred to as decay. So because of this breakdown, when isotopes break down, they are said to be radioactive and unstable. When these isotopes break down, or the decay that they give off, they have three types of emissions: alpha particles, beta particles, and gamma particles. Alright, so alpha decay. The alpha decay refers to the alpha particle which is released, and the alpha particle, when released, causes the mass number of the atom to increase by 4 and the atomic number to decrease by 2. The helium nuclei that is released has a positive charge, and this positive charge is a 2 plus charge. Alright, so this is what our helium looks like. You see here, and this is how we will calculate it. This is how we will calculate things. So we have uranium U, and that has a mass number of 218, and it has an atomic number of 92. And we see that when it emits alpha particles, our atomic number changes from 92 to 90, and our sorry, I put the wrong thing. It's supposed to be 22, right? And our sorry, I put the wrong thing again. Alright. Alright. On in life. So we actually go from 218 to 214. And so we go from 218 to 214, and we go from 92 to 90. And that's how our decay works. So for example, if we have something simpler, let's use magnesium, it should be 24 and 12. And we have, if we have a decay, we will have our 4, we have 2, we have He, we will have an atom that then has a mass number of 20 and an atomic number of 10. So our next emission that we have is a beta particle. In a beta particle, the mass number remains the same, but the atomic number increases by 1. These particles are formed when a neutron disintegrates, producing a proton and an electron. Alright, so here we see our neutron that is forming 1 proton and 1 electron. And then we have the isotope of Na, where we have our atomic number as 11, and we have, so when we add an electron on, when we go through our beta particle emission, by the way, this is how we write beta, a B kind of like with a hook at the bottom, we see that our atomic number increases by 1, but we see that our atomic number increases by 1, but our mass number does not change. Our next radiation type is gamma particles. Gamma particles do not change the mass number or the atomic number. They're just released. And here we have our example. We have iodine, which will be I, 125 and 55 at the beginning, and we say it's 125 and 55 at the end, with our gamma particle being released. Our next thing is that we have electron capture. Electron capture is where a proton is converted to a neutron. Therefore, the mass number stays the same and the atomic number decreases by 1. Alright, and that's where we have our example. So, radioactivity and uses of the radioisotope. So, there are many uses of radioisotopes, and these are just a few that I have put on the next 2 slides. There is carbon dating, where all organisms which are alive have a specific amount of concentration of carbon-14. So when the organism dies, there's a decay of the body, and therefore a decay of the carbon-14, which decreases the concentration of the carbon-14 within the body. So the concentration of the carbon-14 within the body of the dead organism is then tested, and that is the concentration that we obtain is used to determine when the organism died based on the rate of radioactive decay. We have several medical applications for the radioisotopes that we use in the medical field. Some of these are sterilization and surgical equipment, locating cancerous tumors and other medical issues, bone imaging, radiotherapy, and this list goes on and on and on, because there are countless amounts of things that we use radioisotopes for. Tracers. Radioactive tracers are used to locate leaks in pipes. They're used, radioisotopes are used in smoke detectors. This is AM241 americium, which is radioactive, and food that we eat goes through a process called food irradiation, and this is where we use gamma rays to sterilize food and increase the shelf life of the food. So we have another type of radiation, which is electromagnetic radiation. Electromagnetic radiation is viewed as a stream of photons. These particles have no mass and travel in a wave-like motion at the speed of light. So because they travel in a wave-like motion, they are then given a wavelength and a frequency, and this is given by the equation C is equals to V lambda, where C is equal to the speed of light, which is a constant, as given by 3.0 by 10 to the positive 8 millimeters per second. We have V, which is representative of the frequency, and lambda, which is representative of our wavelength. Another way that electromagnetic radiation occurs is when you pass on electric discharge, which is also known as a current, through its vapor. If this light is observed through a spectroscope, we will see a series of lines. And remember Don Niels Bohr? He proposed a way to analyze and interpret these lines, and he said that the electrons can only occupy a certain fixed energy around the nucleus and can be visualized as orbitals of increasing energy. Alright, So our first example will obviously be the simplest example that we have and that we can use, and that would be hydrogen. Hydrogen has only one electron. However, hydrogen has an infinite number of orbitals. Okay, so even though we have one electron, the electron can still be excited and can still occupy these orbitals. Obviously only one orbital at a time, since this has to be since it's a fixed place that it has to be in. Alright, so when hydrogen is excited in a discharge tube, the electron promotes itself from the lowest energy where it probably is and which it occupies normally up to a higher energy level. After the excitation, or the energy from the excitation is gone, the electron will then drop back down to its lower orbital through a series of steps, or it will directly drop back down. Alright, at each step or at each level that it reaches, it gives out a quantum of energy, and is given by the equation E equals to hv. So where E is the energy, H is Planck's constant, and V is the frequency. So the energy released from the electrons is shown by the lines on an electron spectrum. So when the electrons drop to level 1, it gives rise to the Lyman series, and when the electrons drop to level 2, it gives rise to the Balmer series. So I'll just let you look at what we have here. We have on the yellow, we see that all the electrons drop from the different electron levels. So n equals to 1, n equals to 2, and those are the orbitals that it could be occupying. So it drops from each orbital all down to 1, n equals to 1, and that gives rise to the Lyman series, as we said. And we see that in the Balmer series, we have a drop from all of these orbitals, n equals to 7, n equals to 6, n equals to 5, n equals to 4, n equals to 3, all to n equals to 2 and no lower, which gives rise to the Balmer series. Electrons can be thought of as waves, as we've seen from electromagnetic radiation, and thus they can be represented by a Schrödinger equation. We don't have to know the equation, but we have to know what the equation tells us. So this equation describes an atomic number in 3 quantum numbers. The first one is the principal, which is n, the angular, which is L, and the magnetic quantum number, which is m. The principal quantum number describes the energy level of the electron. The maximum number of electrons in n is equals to 2n squared. So we have our energy level, which is equals to 1 here. So the maximum number of electrons that we could have is 2 multiplied by 1 squared, which would equal to 2 times 1, which would equals to 2. So that's our number of electrons. So let's try it for n equals to 4. We will have 2 times 4 squared, which will equals to 2 times 16, which would equals to 32. So that could be our number of electrons that we have at n equals to 2. The angular quantum number L describes the sublevels in n and the shape of the orbitals. These sublevels are given the letter designated S, P, D, and F. When we see, and so our principal quantum number, when our principal quantum number is n, we have one sublevel, and that sublevel's name is 1s. When our principal quantum number is equals to 2, we have 2 sublevels, which is 2s and 2p, and when it's equal to 3, we have 3 sublevels, 3s, 3p, and 3d. Alright, and the magnetic quantum level gives the number of orbitals within each sublevel. So S has 1 orbital and can hold a maximum of 2 electrons. P has 3 orbitals and can hold a maximum of 6 electrons, D has 5 orbitals and can hold a maximum of 10 electrons. So what are the shapes of these orbitals? Each subshell contains one or more atomic orbital. Each orbital can hold a maximum of 2 electrons, and below are the shapes of the orbitals. It should be noted that each subshell has an s orbital, and as the energy level increases, so does the s orbital. So what we have here is we have S. So we have our axis. We have S. This is our Z plane. This is our X plane. This is our Z plane. And our S is in a circle occupying our plane. Alright. We have 2PZ, which goes like this. And that's because it's primarily on our Z plane. We have 2PX, and that's because it is on our X plane. And we have 2PY, and that's because it's primarily on our Y plane. So how do we fill our electron configurations? So as you remember, before we had our electron configurations, we had 2, 8, 8, and that's how we will rate our electron configurations before. However, now we'll be rating our electron configurations, assigning each electron to its own orbital. So in doing this, we have to first draw our electrons. It must be noted that when we're placing our electrons have spins, and so spins cannot. So if you have an arrow up here, this is how you represent the electron, and you have an arrow pointing upward, you cannot have two arrows pointing upward within the same box for your electrons, for your electron configurations. Your spins must be opposite one another, because light forces repel. And so we think of this as a negative charge and a negative charge, who want to be as far away as they can be from one another. When we're filling our electron charges, remember that we have to fill them one at a time. Only 2 electrons can occupy an orbital, and electrons fill degenerate orbitals with the same spin, one at a time. So our degenerate orbitals will be our p orbitals and our d orbitals. However, for now we'll be dealing with our p orbitals. So if you have 2px, 2py, and 2pz, you first start with 1, 2, 3, fill those first, and then you could come in and add each one that can hold 2. Alright, so our first one will be nitrogen. Our first practice question will be nitrogen, and we remember that nitrogen has 7 electrons, and so we'll have to fill it first. Fill it. And so our first thing will be to label what we have here. So we have our 1s, we have our 2s, we have our 2px, our 2py, and our 2pz. It really does not matter which order you put in your x, y, and z once you filled it correctly. Alright, so we have 7, and we have 7 electrons. So our first thing would be that we have to fill our 1s orbital. So you fill it 1, and then we put another 1. That's 2 electrons that we have within our 1s orbital. What we have after will be 1 because we have an S, and because this is not degenerate to the p's, we will have 1. So that's 4 that we have so far, 4 electrons. So because we have p and our p's are degenerate, what we'll do is that we'll fill them each, and we'll count how much we have to ensure that we have all, and then we'll move 1, 2, 3, 4, 5, 6, 7 electrons, all accounted for, all arranged properly. And so we'll say that our electron configuration for n is equals to 1s, 2, 2s, 2, 2p3. And that's because we don't account for the x, y, and z. We just say that they're all a part of 2p, and we say we have 3 electrons in. So when we have what we're placing at top, we have how much electrons is inside of our orbital. So with we have 1s2, that's because we have 2 electrons within our 1s orbital. 2s2, we have 2 electrons within our 2s orbital. And in our 2p orbitals, even though they're not all inside of the same electron box, they are, however, within the 2p orbital. So let's try for oxygen. Alright, so we have the same thing, 1s, 2s, 2px, 2py, and 2pz. Alright, oxygen has 8 electrons, and so we'll fill our first 1, 2, that's 2 electrons that we've accounted for, 3, 4, 5 into p, 6 into y, 7 into pz, and into px, 8. So we'll say that O has an electron configuration of 1s, 2, 2s, 2, 2p, 4. Alright, I think we could do another one just to ensure that everybody has it. And so we'll try F. Right, and so let me join our 2 p's. And so we know that the number of electrons that F has is 9 electrons. So let's start 1, 2 in our 1s. In our 2s, we'll have 1, 2, so that's 4. And we'll fill these individually. 1, 2, 3, 4, 5. So then our electron configuration for F will be stated to be 1s, 2, 2s, 2, 2p, and we have a cumulative value of 5 within our 2p orbital. And that is it for today.